Video we will look at a interesting problem based on current mirrors. Before looking into this problem, we'll have a look at the regions of a MOSFET. When will be a MOSFET in saturation region and triode region? If we take a single nmos transistor, ID is given by half mu n Cox W by L into VGS minus VT whole square in saturation region. And the conditions for saturation are VGS should be greater than or equals to VT and VDS should be greater than or equals to VGS minus VT. If we simplify this expression, this comes out to be VD greater than or equals to VG minus VT. This is, let us say I have drain potential VD and gate potential VG. The lower limit is VD is equals to VG minus VT. It can go above this, but the lower limit is VG minus VT. That means VD can come 1 VT below VG. VD can go 1 VT below VG for saturation. If it goes further a VT below VG, that will be in triode region. So the conditions are VGS has to be greater than or equals to VT and VDS should be greater than or equals to VGS minus VT. And for triode region, in triode region, ID will be mu n Cox W by L into VGS minus VT into VDS minus VDS square by 2, and the conditions are again VGS has to be greater than or equals to VT and VDS is less than VGS minus VT. So similarly for PMOS transistor, ID is given by half mu p Cox W by L into VSG minus mod VTP whole square. For VSG, this is in saturation and the conditions are, one is VSG has to be greater than or equals to mod VT. Second one is VSD should be greater than or equals to VSG minus VTP. VSD can be written as VS minus VD and VSG can be written as VS minus VG minus mod VTP. VS cancels out, so this comes out to be VD less than or equals to Vg plus Vdp. So here the upper limit is Vd is equals to Vg plus Vt. We have Vd and Vg. Vd can go 1 Vt above Vg. If it goes beyond this, this is triode. Below this, it is saturation. So similarly, in triode region, ID will be mu PCR W by L into VSG minus VTP into VSD minus VSD square by 2. So for our understanding, we'll look at some simple cases to determine whether the MOSFET is in saturation or not. We'll look at one case for each nmos and pmos. Let us say this is at 2 volts, that 0.5 volts, and this is at 3 volts. First of all, we have to check whether the MOSFET is in on or not, whether VGS is greater than VT or not. Here VGS is 1.5 volts. Let us say VTH is 1 volt. This is greater than VTH. So first condition is satisfied. We have to look out for the second condition, that is VD should be greater than VG minus VT. Here VD is 3 volts, VG is 2 volts, and VT is 1 volt. So this is greater than 1 volt, 3 is greater than 1 volt. So this is in saturation. If this voltage comes to, let us say, 0.9 volts, for this case VG is 2 volts and VT is 1 volt. VD minus VG is 1 volt. This is greater than 0.9. So this is an triode. VD can come 1 VT below VG, that is it can go up to 1 volt. If it goes below 1 volt, it will be in triode region. So here it goes to 0.9 volts, so it is in triode region. For PMOS case, let us say similarly, this is at 2 volts and gate is at 1 volt and drain is at 1 volt. Similarly here VSG is 1 volt, so this is on. For the second case, VD is 1 volt and VG is at 1 volt. Let us say VTH is 1 volt. So VG plus VD is 2 volts. 1 plus 1, which is less than this. So this will be in saturation region, and if this node potential goes to 3 volts, in this case here for PMOS VD can go 1 VT above VG. VG is 1 volt, so it can go up to 2 volts. If it goes to 3 volts, it will be in triode region. The second condition will not be satisfied. So these are the basics needed to determine whether the transistor is in saturation or triode. Coming to this question, we'll see what is the current flowing out. Here we can see that the current flowing here is I, here 0 amps will flow, so this will have a VGS. The same VGS will be there for M1 also, and here also 2I current is flowing from this MOSFET, so this will also have some VGS, VSG, plus minus VSG, same VSG, and we can easily get confused that 2I current is flowing here, so 2I current has to flow from here. I current is flowing from this MOSFET. For current mirror concept, I current has to flow in this MOSFET. Clearly we can see that KCL is getting violated here, so this can't be true. So the fundamental principle here is, let us say, here the main part is, let us say initially both M1 and M2 are in saturation. Assume initially that M1, M2 are in saturation. If we assume that the current flowing in M1 is 2I, the current flowing in M1 is I, the current flowing in M2 is 2I, the current flowing in M1 is I. Let us say this node potential is some X. Because 2I is more than I, you assume some parasitic capacitance here. So more current is flowing into the node than the current drawn from the node. So this node potential will increase. Vx increases. This node potential will increase. This node potential increases. If this node potential increases, M1 will be in saturation. See, for nmos, the limit is on the lower side. If we come below Vg by a Vt, then you will be in triode. You will go to triode region. But here this node potential is going up, so M2 transistor will go to triode region. M2 will go to triode region, and build a potential Vx such that I current flows. This node potential goes up such that I current has to flow from both of them, both the transistor. Then it will settle down to some node potential. Because it is in triode region, it needs high VDS to carry the same amount of current as nmos transistor. This node potential Vx, we can clearly see that 2i is greater than I and this node potential is increasing. It will increase such that it will carry a current I in the triode region. Okay, thank you.